Yes, so my name is Erich Haratsch. I work for Seagate on SSDs, and I'll talk about doing compression inside the SSDs. Actually, I had an interesting experience when I prepared this presentation. I used these nice OCP PowerPoint templates. The size was 5 megabytes, but then the conference organizers want a PDF. So when I converted my presentation into a PDF, it turned out to be 50 megabytes. I still have no clue why. So that's the other example. So I'll talk about the opposite, about data reduction as opposed to data expansion. Seagate actually has an SSD that already features compression inside. And when we offered it in a market, we often get some questions. And I would like to address these questions here to educate the storage community about the benefits of compression, the use cases, and and also the workloads where it works best. So there are two questions that we got quite often. One is whether compression corrupts the data. Of course, when you build SSDs for the cloud, for the data center, you don't want to modify the data. So we talk here about lossless compression versus lossy compression that is used for images and videos typically. Then the other question that comes quite often is whether compression actually may kind of make the data set even larger, like the example that I just gave you in the beginning. And of course, there are also ways to prevent this from happening. So I would like to start with a few words about the compressibility of data. So we have collected within Seagate quite a large data set of files that are used in the cloud and enterprise base. And we've measured the compressibility per file. And then based on that, we computed the average. And you can see here typical numbers for the average compressibility. So we looked at MySQL, Oracle data files. We looked at operating systems such as Windows, but we also have some data for Mac OS. And then we looked also at virtual machines. And the average compressibility we typically see is somewhere around 50 to 70%. On an individual file level, it can vary quite a bit. I mean, you can have individual files that are compressible up to 80, 90%. But then in terms of the average, typically we see between 50 and 70% for these types of data files. Image and video files, of course, they have been compressed before. But the interesting thing is they still may have some little amount of compressibility left due to the metadata that is embedded inside the image and video files. So there, the compressibility can reach a few percentage points. Now, so how do you do compression inside the solid-state disk? As I said before, of course, it needs to be lossless. And there are lossless compression algorithms available. I mean, most of you are familiar with gzip that essentially uses a combination of the Lempel-Ziff algorithm and Huffman coding. Also, when you do it within the SSD, you need to do it inline at full data rate. You can do it if it's part of the SSD controller. The latency that then gets added due to compression is really very small. I mean, it's comparable to the latency that you get due to error correction or due to encryption. So when you compare that latency to the programming times for the media, the read times of the media, as I said, it's quite negligible. Then another question that comes up is, where do you do the compression? It needs to be done before the encryption. Encryption scrambles the data, so after that, the data is typically not, of course, compressible. And then also, you want to do it before the error correction coding. I mean, the error correction is really the last step you want to apply for data integrity reasons. And then when data is not compressible, I mean, you also need to include that feature inside the compression that you then write the original data, not the larger compressed data. Just look at my PDF example in the beginning. And then the benefit is, you write less data to the media. You also read less data from the media. But apart from that, I mean, there are even larger benefits that I will talk about later. So, to the best of my knowledge, there are not many other SSDs around that already do compression inside. I gave Seagate as an example that we have one SSD, and you wonder really why. And I think one reason is that it's quite challenging to implement from a data management perspective inside the SSD when we look at the flash translation layer. The flash translation layer essentially converts the logical data units into physical data units. The logical host pages, they have a fixed size, and then the flash translation layer maps them into the physical location. And these physical units then also have a fixed size, and they fit very nicely into the media, into a flash page on the NAND, 3D NAND media. When you compress the data, when you have these host pages that come in, you don't really know beforehand how long or large the data will be after compression. So you end up then with data units of variable size that need to be written on the media. So that's really the challenging part here, to keep track of these variable sizes and then pack it all together so that it fits nicely on a page in a flash media. So that's the kind of the challenge that needs to be solved then in the flash translation layer of an SSD. So what are the benefits? There are two use cases in terms of using compression. You can use compression to increase the over-provisioning. So here on the left side, you see how data is arranged in an SSD. Typically, you have the logical kind of user data space, and then there's over-provisioning. And then when data is compressed, one way to use compression is then to have additional over-provisioning. And the benefit here is really that it reduces significantly write amplification. It therefore improves performance and also endurance. And I would like to give you here an example. So here you see write amplification as a function of over-provisioning. And you can see as over-provisioning decreases, write amplification increases significantly. And many SSDs operate in this lower OP region, where you can see that write amplification can reach 6 and even higher. But if you have just a little amount of compressibility in the data, 10 or 20%, you can reduce write amplification by a factor of 2 to 3. And then with even higher compressibility, the write amplification reduces even further. So when we talk about write amplification reduction of 3, this means 3 times less writes. So it means 3 times higher endurance. It also means 3 times better random write performance. So there's really a significant benefit here, both in terms of endurance and also in terms of random write and mixed read-write performance. Another way to use compression is to offer more capacity to the user. And this is shown here on the left side. So as I said in the beginning or earlier, in an SSD, you have the logical user data space. You have some space for over-provisioning. And then when you compress data, instead of using then this additional free space for over-provisioning, you could offer this space to the user as additional logical capacity. Here, the thing to notice, the actual logical capacity then depends on the compressibility of the data, and this needs to be monitored. So you may get highly compressible data. You can offer a large user capacity to the host, and then you raise the data, some new data comes in, it may be less compressible, so you need to watch that and then adjust the user capacity accordingly. So it needs to be managed then with the host. Another application for compression is to use compression together with QLC SSDs. So QLC uses 16 levels. So it improves the capacity compared to TLC theoretically by about 30%, 33%. But QLC NAND media typically has some challenging attributes. It has relatively low endurance. The performance is not as good as 3D TLC NAND. And compression can really help here to mitigate these effects because, as I explained before, compression reduces write amplification. Therefore, it can improve the effective endurance of the SSD. It can also improve the performance of the SSD. Or you could use compression combined with QLC to offer high capacity SSDs in applications where data is compressible. As I said before, Seagate has an SSD that features compression. So this, and it's already being offered in a marketplace. So this is a SATA-based SSD. It has built-in compression, as I described it. It has all the other SSD features that you need in terms of security features, quality of service, performance features. And this drive actually won the Best of Show award in the Flash Memory Summit last summer. So it's available, for the OCP community to use and to deploy. So here, the call to action, So as I said, compression is not widely used yet in SSDs. So, I would like to propose that we add compression-enabled SSD devices to the OCP, to the Open Compute project. And we should define use cases, workloads, interfaces. We should define guidelines how to specify performance, endurance, and quality of service of compression-enabled SSDs. We should define workloads to benchmark compression-enabled SSDs. And here in particular, also what is very important, how to generate data at certain compressibility levels so that you can really do apples-to-apples comparisons between different devices. We should educate the OCP community about benefits. And as a result, I think we would have another tool to optimize SSDs in terms of performance, endurance, and capacity. So that's all I had. Thank you for your attention. And if you have any questions, please go ahead. There's one.
You mentioned using it for compression for extra user space.
Yeah.
How does that relate back to or how do they take advantage of that? How does the application and the system take advantage of the extra space? Or how do they access it?
Yeah, how they access, how do they take advantage of it is, of course, taking advantage of it in terms of having more capacity. But you need to, as I said, there needs to be some interaction between the host and the SSD device to monitor what the free space is and then kind of adjust the behavior accordingly. So, yeah, please.
I'm trying to reason about why at 10% the write amplification dropped that much. Because at 10% compression, you have so much fragmentation.
Yeah.
So what's the inherent reason? There's a big gap in reduction in write amplification. A follow-up question is, does that mean if I have no compression, but then I reduce my workload by 10% or increase my overprovisioning by 10%, can I reduce the write amp at the same level?
That's right. So as you said, if essentially what compression does is that it offers additional OP to the drive. So if you had additional OP, the write amp would reduce accordingly. And it's due to the garbage collection, that when you are in a low OP environment, that the write amplification then explodes. Yeah.
So a couple questions. Where do you see this most commonly used? And then on top of that, you mentioned the previous question, monitoring. Is that a vendor unique thing, or is it something you bounce back off of the command completion?
Yes, ideally it would not be, I guess, as part of this OCP effort, not vendor unique. So that's part of the call to action, to define kind of vendor agnostic mechanisms to make this happen. So I'm open to any input that you all may have. And then in terms of, the use cases, is when you look at these workload types, data is highly compressible. We also heard in a keynote talk yesterday, data is exploding. So there's really an urgent need to reduce data. And the way to reduce data is by compression or deduplication. And that's what this is about, especially for these workloads that are really highly compressible, metadata, OS files, database files, to use compression to reduce the data sets.
This is where you actually see it being deployed.
Yeah.
These are not just hypotheticals.
No. So, and it's a real product already being used for these types of applications. Any more questions? Okay, thank you for your attention then.